Hello, my name is Henning Lange. In this video, I would like to give a quick overview of a paper that we just released on the arXiv. In this paper, we explore the application of series expansions and fast summation algorithms in the context of machine learning. Specifically, we introduce fast computational layers that can be used within neural networks. We introduce one explicit layer that outputs function values at specific spatial locations and two implicit layers. Both of the implicit layers output quantities along an array. The root implicit layer outputs the distance between a pinhole camera and an object, whilst the integral implicit layer outputs line integrals along an array. All of these layers are fast in the sense that they operate in an unintuitive complexity class, thanks to ideas adapted from the fast multiple method that finds application in high-performance fluid solvers. Whilst most existing approaches scale multiplicatively, our approach scales additively in the sense that once the price for computing a series expansion has been paid, obtaining the value of a pixel is independent of the number of model parameters. Our base model is a spatially continuous convolutional operator similar to a radial basis layer. In every iteration of the backpropagation algorithm, in the forward pass, we expand this operator into a voxel grid that contains 3D Taylor series expansions at voxel centers. During the backward pass, in order to compute the required Jacobian vector products, a second expansion is computed. This oftentimes entails inserting quantities related to the tangent vector into the expansion. Since the implicit layers output quantities along an array, during the forward pass, the voxels that intersect this array are enumerated, and because Taylor series expansions essentially are a local polynomial approximation, any line through a voxel can be converted to a univariate polynomial. Similar to Fourier space, in which certain operations such as convolutions are sometimes easier to compute, in Taylor space other operations can be performed elegantly. The root implicit layer exploits the fact that analytical and fast solutions for root finding of polynomials of order 4 or less exist, while the integral implicit layer exploits polynomial closure. That is, polynomials can be multiplied, composed, and integrated easily. Our techniques can lead to a massive reduction in flops in comparison to implicit approaches based on neural networks. A single implicit layer can be used to model signed distance functions. Training this layer on 10 million samples reduces the number of flops required per epoch by approximately 200-fold compared to the DeepSDF architecture. We combine the root implicit and explicit layer to represent RGBD images. In this case, the root implicit layer models depth, whereas the explicit layer handles color. The animation shows a rendering of a single RGBD image from novel viewpoints. We use a single integral implicit layer to train a radiance field. Specifically, we train this layer based on 2D images annotated with viewpoints. This layer offers an approximately 150-fold reduction in flops compared to the neural network-based approach per epoch, but currently results in a loss in accuracy we believe to stem from enforcing a non-negativity constraint in a crude way. The previous experiments showcased applications of a single layer in isolation. However, the computational layers introduced in this paper can be used in conjunction with regular neural networks. In the following experiment, we train a convolutional neural network to output the parameters of the proposed root implicit layer that induce a desired depth field in an autoencoder fashion. The panel on the left shows the input and desired output. The middle panel shows the depth field as predicted by the convolutional neural network, whilst the right panel shows a retouched version of the same frame. Retouching is done by additional steps of gradient descent without the neural network. Training a neural network to predict optimal parameters of the layer amortizes the optimization procedure and significantly reduces the time to obtain a given depth field whilst increasing the error. Note that this paper lays the mathematical foundation of the application of fast summation algorithms and series expansions in the context of machine learning. The current implementation is flop inefficient, and a careful implementation of the techniques in a low-level general-purpose GPU language could still significantly reduce training times. Expanding the operator currently takes 300 milliseconds per channel, whilst rendering an image given the expansion currently takes 250 to 600 milliseconds depending on the layer. This cost can be reduced to approximately 15 milliseconds for the expansion and rendering times of less than 100 milliseconds. To conclude, this paper introduces algorithms that reduce the computational complexity of training implicit models in the realm of computer vision and graphics. We propose 3 types of layers that are very expressive. A single layer is comparably expressive as an entire neural network, while significantly reducing the computational cost for training and inference. However, the current implementation is only approximately 2% flop efficient, depending on the layer, but because all of the kernels are compute-bound, we believe that a flop-efficient implementation is possible. At this time, we believe that the techniques introduced in this paper allow for training a radiance field in the matter of minutes as opposed to hours, with a similar accuracy as the neural network approach. Thank you for your attention.